Hi everyone. Today we will be talking about the operation of multiplexer, and to give you a better understanding how multiplexer works, I created this image. You could think about multiplexer same as you could think about some kind of switch, but in this case our switching circuit has multiple inputs and one output. And what multiplexer does, it connects one of these inputs to the output. Of course, we need some kind of signal that says to this switching circuit which particular input will be connected to the output. And this is the purpose of this signal here. And let's call it selector signal input. Now what the signal does, it simply says to the switching circuit which of these inputs will be connected to the output. Now what could be the possible application for this kind of circuit? Let's imagine that we have three sensors. Temperature sensor, wind sensor that measures the speed of the wind, and air humidity sensor. And we want to store this information from these sensors to some kind of storage device. If we wouldn't have our multiplexer here, our storage device would need three inputs, one input for each of this sensor. But because we have multiplexer, we need only one input to our storage device to get the information from all of these three sensors. Of course, there are a few considerations that we have to think about before using multiplexer, and one of those would be, the most important actually, would be how fast our input signals are changing and how fast we can transfer this information using multiplexer to our storage device. Now, if our input signals are switching very fast, this could be a problem, but in this case, because the temperature, the speed of the wind and air humidity, those are not things that are changing very fast, we don't have to worry about we don't have to worry much about the speed. Let's look at the simulation of multiplexer. Here I have my multiplexer. It has 4 inputs and each input is 4-bit input. Because of that, we have 4 zeros and ones at each of these inputs. And because we have 4-bit inputs, we also need 4-bit output so that we would be able to represent our signal. Here I have my selector input, and this selector signal is 2 bits long. Why 2 bits? Because we need 2 bits so that we would be able to create 4 unique combinations of zeros and ones. And because we have 4 inputs, we need these 4 combinations so that we could represent their position. And the last input is the output enable input. And what this input does, it switches the output of multiplexer from low impedance state to a high impedance state, and from high impedance state to low impedance state. So let's enable our output. To enable our output, we have to switch the signal from 0 to 1. And now we can see that we have connected our output to the first input. And to prove to you that we have connected to the first input, first of all, we can see that this bit combination is the same as here, and when we are switching this combination, we can see that also the output is changing. Now, if we change our selector bits from 0, 0 to 0, 1, we can see that we have connected our output to the second input. If we are changing now to the next combination to 1 and 0, we can see that it has connected to the third input, and if our selector signal is 1, 1, then we can see that our output is connected to the fourth input. There is one last thing that I would like to do, and that is I want to simulate our multiplexer and I want to fill out its truth table. This is one of those cases where I started with a more complex example of multiplexer, just because in my opinion that was a much better representation of the functionality, how multiplexer exactly works. But in this case our multiplexer has not 4 inputs, but it has only 2 inputs, and each input is 1-bit input. Because we have only 2 inputs, also our selector input signal is 1 bit long, because we need only 1 bit so that we could represent the position of our first and our second input. If we look at this truth table, we can see that we have no output enable bit here. That is only because I wanted our truth table to be as simple as possible, and in this case we will assume that our output is all the time connected to our inputs, and in this case our output enable bit has to be 1. And now let's look at the first case. In the first case, our select signal will be 0, and we know that if select signal is 0, our output is connected to the first input. And if select bit is 0 and our input signal is 0, then we can see that our output signal also will be 0. In the second case, our select signal will stay the same, but we will change our first input signal from 0 to 1. And we can see that also our output signal became 1. So we have to write here 1 and 1. In the third case, we will change our select signal from 0 to 1, and we can now, because our output is connected to the second input also, and the second input signal is 0 at this moment, also our output signal is 0, so we have to write here 0 and we have to write here 0. And the last case will be when our second input signal is 1, and we can see that when this input signal switched from 0 to 1, also the output signal switched from 0 to 1. So we have to write here 1, 1, and also here we have to write 1. Now you could have question what we will do with these empty places here. In those empty places we will write X, and what this X represents, it simply says that it doesn't matter what will be the input signal at this particular case, it won't have any effect to our output signal. To show you this, let's look at our first case again. Okay, so let's switch our select signal to 0. The signal to our first input will be 0, and we can see that our output signal also is 0. And it doesn't matter how I change this input signal to the second input. The output signal all the time stays the same, and this is why the second input signal is unimportant at this moment, and this is why we write here X. That's it for this video. If you liked it, then press that little like button, and see you at my future videos. Bye.